is Colin Camerer. He's from Caltech. Thanks a lot to be here. I suppose you are under jet lag, and we appreciate the fact that you crossed the Atlantic Ocean from California. You have a good spring weather, so maybe yes, okay. It's a compensation. So I'll leave you the floor. The title of your talk is Neural Correlates of Risky Choice.
Right, so once again, I've changed the title quite a lot. Thank you very much for... yeah, I'm sorry, it's actually quite a different talk. I partly, as Peter said, to try to coordinate with him and talk about something a little more thematic. So thank you very much for arranging this. This has been a terrific day so far, and I'm very happy, even though it would be nice to have a shorter trip, I'm very happy to have come. So I'm interested, today I'll speak about the cognitive neuroscience of strategic thinking, mostly about cognitive, and just a little bit about some quite simple and very preliminary results subject to all the usual caveats from fMRI. So specifically, I'm going to focus on strategic thinking, which is reasoning about what others will believe, value, and choose. And I'm going to draw a kind of coarse distinction between what's called equilibrium game theory, which assumes that players, either through introspection, maybe talking, trial and error experience, or maybe formal training, come to correctly guess what other players will likely to do, and contrast that with an approach we call cognitive hierarchy, which is, in a sense, is a cognized version of something like rationalizability, as those of you who are experts will see. Okay, so the essence of the equilibrium concept, for which John Nash won the Nobel Prize in the 90s, shared the Nobel Prize, is the two properties, which is first that choices are optimal given beliefs, second that beliefs about others' choices are accurate. And again, it's always been a little bit of a mystery in game theory about how this accuracy comes about, whether it comes through a learning process or something like that. But it's just a mathematical thing, a fixed point theorem. And by the way, the optimality of choices can easily be relaxed and replaced with something like a softmax or stochastic choice process, and that results in something called quantum response equilibrium, which is widely studied in behavioral game theory too, particularly at Caltech and other places. Okay, in the cognitive hierarchy approach I'm going to use, one can think of many variants of how to do this, and I'm just going to hone in on one because we've applied it to lots of different types of data. But there's lots of interesting questions about generalizability of the structure. Is one in which you start somewhere in the hierarchy with what we call zero-step players. They're assumed to do something very system one and simple and heuristic. Probably they have much quicker response times. Usually they do when we measure them. They're not thinking necessarily about another player. They're doing something very automatic and heuristic. It could be, say, randomizing across a set. It could be picking something that springs to mind, something that's in a geometrically focal location or something of that kind. In one interpretation by Vince Crawford, who's done a lot of research here, they're basically just a kind of like yeast, in the bread. They're just... it might even be a figment of the other players' imaginations. That's just some way to begin an iterative process of reasoning. The K-step players guess accurately what the lower step players do, but they think they're the only K-step players. There's a kind of overconfidence or maybe non-self-awareness. So one-step players think they're playing zero-step players, and then they optimize. Two-step players think they're playing 1 and 0 and optimize, and so forth. And then, as you'll see, there are lots of natural ways to truncate the hierarchy in some reasonable way. So the plan of my talk, first I'm going to start from less neuro to more neuro, with behavioral evidence from a bunch of interesting games, just showing how this type of cognitive hierarchy approach might work and why we think it helps us explain some puzzles. I'll say quite a bit about eye tracking, a little bit about imaging, and some more complicated things at the end. So behavioral evidence. The first game I'll start with, I'm going to start from easy to hard. By the end of the talk, we'll be doing what actually is quite complicated game theory. In this so-called beauty contest game, players choose a number from 0 to 100. Everyone's doing this simultaneously. The closest to 2/3 of the average wins. It doesn't have to be 2/3, but that number's been used in a lot of games. And what you'd like to do is to be, if you think of numbers going from 0 to 100 as being low to high, you'd like to be lower than most people, but not too low, because you want to be 2/3 of the average. No lower, no higher. So there are a lot of experiments on this. I'll start with one that we did in 1998 with students in Singapore. And the way a lot of people think about this is to say, I'm not sure what the number will be. The average of numbers from 0 to 100 is 50, so I'll choose 33, which is here. But wait a minute. If everyone picks 33, I should pick 2/3 of 33, which is 22, which is here. But wait, if everybody picks 222, I should choose 2/3 of 22, which is around 15, which is here. And in equilibrium theory, this iterated process of reasoning doesn't stop until everyone is doing what they think everyone else thinks everyone else is doing, and so forth, which in this game is at 0. That's the unique Nash equilibrium of this game, which happens to be on the boundary. So in this diagram, from my paper with Ernst Fair in Science, reviewing lots of different studies, the equilibrium prediction is here. In a way, it's unfair to beat up on that prediction because it's so extreme, it can only be wrong. And what you see in the data from Singapore is a series of spikes in the middle. There are some people who pick 0. They don't win. That's important too, right? So if you think of game theoretic advice is supposed to create value, picking 0 is not the right answer to the question, how do I make money in this game? It is the right answer to the question, what's the Nash equilibrium? But those are two different things. It's also the right answer to the question, when the game is played over and over, what do numbers converge to? So it's the right answer for something, but not necessarily the best model of human behavior when people play for the first time. And they're also, when we run these games in large samples, you also get interesting quirks which are hard to account for by any parsimonious theory. Like there are a number of people who chose 80 and 88, which are dominated. You're never going to win with those. And that's because in the number 8 is superstitiously believed to be good luck in Chinese, and this was in Singapore. So it was not good luck for them. So there are lots of quirks in these theories that you might need to add in very special properties. These are 8,000 observations pooled from 3 different newspaper and magazine contests where people had to write in, and the winning answer got to win some prize. Like Financial Times, it was first-class airplane tickets from London to New York. And this is nice because these are average people, well, not actually average people, the readers of these magazines who are self-selecting. And you can see they show roughly a similar pattern to the students in Singapore. Okay, this is Reinhard Zelton, who shared the Nobel Prize also with Nash. And he said, and Harsanyi, he said that the natural way of looking at game situations is not based on circular concepts, but that he means this fixed point, that I'm optimizing given your choice, and your choice is the optimal one given my choice, but rather on a step-by-step reasoning procedure. And he had in mind, I think, something very much like this cognitive hierarchy. Okay, so to remind you, we need several pieces. There's a distribution of the steps of thinking f of k. The 0 steps choose in some heuristic way. Ideally, that would be the same in every single game, but there are obvious reasons why it may not be. If you really think it's something heuristic, like a snap judgment or a system 1, it could well vary across different games. It could be a lucky number in one game, and it could be an average in the other games. The k-step players think that others are below them. There are 2 flavors of this model. The one I'll talk about, we call CH, is that you take the actual distribution f of k and just truncate it, censor it from k minus 1 to 0, and then normalize, so that the higher level players actually have the right model of the world. As they go higher and higher in reasoning, they're converging to the correct distribution. Another version is that everyone who's at level k thinks everyone is just one level below them. In different mathematical applications, some of these turn out to be easier or harder than others. What is f of k? Well, you could either estimate it parametrically. We did that in some early work. Or you can parameterize it. We've found it very useful to use the Poisson distribution. First, it has a fancy French name. Second, it's parameterized by a single parameter, tau, which is the mean and the variance. So that's very handy if you're trying to do mathematical economics. You just have one parameter to study. It also derives from this property. If you think of transitioning from k minus 1 steps of thinking to k, it's like sort of graduating, at a harder and harder university or school system. Then if f of k divided by f of k minus 1 is proportional to 1 over k, that is, as you're going up this hierarchy, it's less and less likely you'll transition from one step to the next. That implies the Poisson distribution. And here's a graph of various values. A value we find useful in a lot of experiments is around 1.5 in red. The mode is at 1 step of reasoning. That is, people are optimizing against a random distribution or a heuristic distribution. And the nice feature is that because of the mathematical structure, the Poisson drops off very, very rapidly with high steps of reasoning, which we think is something like working memory constraint or some kind of algorithmic computational constraint. Okay, now I'm going to start very far from the brain in Sweden and talk about a field, non-experimental field data set, which just shows some of the interesting properties of this theory, and then I'll eventually hone back in. So this is a lottery ticket you could fill out in 2007 in Sweden. And in this special type of lottery, you choose a number from 1 to 99,999, an integer. The form is such that you can pick up to 6 different numbers if you'd like and fill out the forms. The lowest unique number, that's why we call it loopy, lowest unique positive energy, loopy, wins 10,000 euros. On average, 53,000 people played every day. There's a TV show, if we had more time I would show you, there's a TV show that shows the numbers that were chosen starting from the top going down. It's actually quite exciting because it stops at a certain number that's unique, but you don't know if that's the lowest unique one that keeps going. And there's some elegant game theory here that my collaborators did. It turns out it's computationally impossible, at least with us using modern computing, to solve for the mixed strategy in Nash equilibrium. The reason is the combinatorics of computing the unique numbers is extremely difficult. So with 50,000 players and 100,000 numbers, it's impossible to do. So we don't know what the Nash equilibrium is. But if you assume that the number of players is not the same every day, and that distribution itself has a Poisson distribution, that is, it's an average of 53,000, but sometimes it's 60,000, sometimes 40,000, then the Poisson game is actually quite easy to compute. A little bit of math gets you this condition. This is a condition on the probability of choosing number k and number k plus 1. E shows up in here. It's just a coincidence this is Poisson again. It's like double Poisson. Simply proving that deriving the equilibrium is kind of a new contribution. Nobody had done this before, including the designers of the game. So here's some data from the first week, which is around 400,000 observations. First, this is the full distribution, 0 to 100,000. The Nash equilibrium is here in black. It basically predicts people should pick about from 1 to 5,000 about equally often. And then there's a very sharp kind of magical drop at 5,518. And then very few numbers should be chosen out here. And the theory looks pretty good. So notice that the theory right away tells you that 95% of the numbers should rarely be chosen. And that's correct. However, if you zoom in on the lowest 10,000 numbers, which is we've done here, this is only the lowest 10% of the numbers, you can see that while the theory's on the right track, lower numbers are chosen more often than high ones. Very low numbers are chosen way too often. Medium numbers from 2,000 to 5,000, not often enough. This is the actual data, and this is Nash equilibrium, the Poisson-Nash equilibrium. And then numbers that are higher are chosen too often. So this can't just be sampling error, right? It's very low numbers too often, very high numbers too often, medium numbers not quite enough. Okay, so we fit the cognitive hierarchy model I mentioned earlier, assuming that the level 0 player is purely randomized and assuming a softmax stochastic choice function rather than best response. And what we get is a fit of tau is 2.98, around 3 steps of reasoning on average, and that fits quite nicely. Specifically, it explains the key features of the data. Number 1, the theory is not bad. It does predict a lot of low choices, and that's what you see. Number 2, you get too many lows, not enough middle, and too many highs. Okay. Then we did some lab experiments. Because this game in Sweden is so simple, we can just play the same game in the lab with a few simplifications. The major one is that we don't have 53,000 people. That's 50 times the school at Caltech. We have 26 people, and they choose numbers from 1 to 99. Here the theory predicts this dotted line. It's kind of similar in shape. It predicts that only numbers from about 1 to 13 will ever be picked, and then the higher numbers won't be. And it reproduces basically the features of the data, but in a weak form. There's too many low numbers, not quite enough medium numbers, and then too many high numbers. Okay. If you're curious what happens over time, by week 7, that's 49 days of play, with the number being announced on this TV show, the theory is starting to look pretty good. And the only real gap between the prediction and the theory, other than a lot of spikes, is in here. So I regard this as actually, Nash equilibrium is doing extremely well here in a very surprising way, and it makes a very bold, counterintuitive prediction. Okay, eye tracking. So the first kind of real cognitive tool I'm now going to show you to try to calibrate this cognitive hierarchy reasoning model, which seems to predict some field data modestly well, is eye tracking. This is the version we use. It's kind of an old, crude version, mobile eye link we use at Caltech. It also records pupil dilation, which is useful as an omnibus measure of arousal sometimes. First thing is, this is a very typical pattern of looking. This is an unusual type of matrix. Those of you who are game theorists, this is a Stroop task, basically, because what we've done in this board is, player 1 is the person who's going to be eye-tracked. They have to make one of 4 choices, row 1, row 2, row 3, row 4. So they're going to eventually choose one of these boxes. These are the paths they get if they choose this row, and the other player, player 2, chooses C1, C2, C3, C4. So that one player chooses a row, the other chooses a column. This is player 1's payoffs. These are player 2's payoffs. They're separated physically, so that in eye tracking we can see if they're going back and forth and comparing. And the main stylized fact you should see is that they're looking at their own payoffs quite a lot more often than the other player. In the study I'm going to talk about in a minute, the difference is about 4,000 milliseconds versus 2,700. So remember, to compute Nash equilibrium, you need to look at your own payoffs and the other players' payoffs. And players are a lot of times players barely look at the other players' payoffs at all, which is consistent with level 0, and level 1. So we can't say, oh, this is a level 1 player simply from these data, but it's consistent with what we get from that story. Okay, this is an older study of ours going back almost 15 years. This is a study on bargaining. I'll sketch it very quickly. It's based on what's called alternating offer three-stage bargaining in this case. In the first stage, the players have $5 to split. Player 1 makes an offer to player 2. Like, you get 2, I get 3. If player 2 says no, the amount shrinks to $2.50, and then player 2 gets to make a counteroffer, an alternating offer. If player 1 says no to player 2's counteroffer, it goes to a third stage. The money shrinks further. It's sometimes called shrinking pie or shrinking cake bargaining. And they have only $1.25 to divide. If that's rejected, there's no money at all. Okay? And the standard theory of this type of game, if players are purely self-interested and they're not concerned about fairness, is that you should look ahead to the third game, figure out what to offer, use that as an input to figuring out what player 2 will offer in the second round, and use that as an input to figuring out what you need to offer player 2 in round 2, a process called backward induction or dynamic programming. Okay, so this is an icon graph. Well, first let's look at the data. These are histograms of how much is offered. In this particular game, the subgame perfect solution is to offer $1.25. Because if player 2 is self-interested, she would see $1.25 is half of $2.50, and if I go to the last round, that's the most I could get. So I should accept that. What you see is that these players here, we call them zeros. You'll see why more in a second. These players here offer, this is a reverse graph. Here's $1.25 on the left. That's the prediction of the self-interested equilibrium theory. Here's $2.50. That's an equal split. They offer an amount that's around $2. So there's somewhere between equal split and the equilibrium prediction. And what the icon graph shows you is how much they're looking at these 3 amounts. The 3 amounts were varied each time, so they can't remember that. They have to look. The width of this icon graph is the number of times they looked at that box to see what was in it. The height of the blue part is the normalized amount of looking time, and these arrows represent the normalized number of transitions or saccades back and forth between the boxes. So what these zeros are people who looked mostly at the first amount, less at the second, and less at the third. They're literally not looking ahead, looking into the boxes that tell them what would happen if their offer was rejected. These are players who spontaneously actually look at the second amount more than the first, and they make a lot of transitions back and forth. They seem to be looking one step ahead. They're saying, if my offer is rejected, what happens next? And they offer much less, closer to the perfect equilibrium. These are players who actually play close to equilibrium, even though they're not that close, and they're looking at the third box a lot and making a lot of transitions from box 3 to box 2 when they're in the first round. And then these are trained subjects. These are subjects who are given a couple of paragraphs of backward induction instructions. They're just there to show that you can't actually compute this equilibrium solution if you need to. So it's not that it's so computationally difficult. It's just somehow unnatural or inaccessible, or system 2. It requires a real leap of insight. Gee, I should look ahead. Okay, here's a class of games that involve conflict of interest. And these are sometimes called strategic information transmission games. There's probably a nice phrase in French. We might call it bullshit games in American. And this is a wide class of games that's been used a lot in economics and political science. You'll see why in a minute. So a sender learns a true state. It may be, say, the value of a stock or the condition of a car they're selling. And it's an integer 1 to 5. The sender then sends a message to the receiver. It might be, oh, this is worth 4. The receiver gets the message, but does not learn the true state. That's the key. So it's like going in for an operation or having your car worked on and saying, how sick am I? How much do I need to pay? How bad is this problem? How good is this stock? And the receiver then chooses an action A, which is, again, an integer. And the conflict of interest is that the receiver wants to choose an action which is equal to the state. They want to sort of know the truth and use it. The sender wants them to choose an action which is the state plus 1. The state plus 1. For example, the sender might want a buyer to pay too much relative to true value, okay? So you can think of lots of examples of this where people are exaggerating the truth in order to get you to go along with some program in politics or economics, or academic politics and economics too, okay? But keep in mind that this structure, as is typical in these game theory experiments in economics, this structure is not learned but is completely told to the subjects. So if the sender says to you, the state is 5, you could say, wait a minute, that probably means the state is 4, you added 1 on. But wait a minute, if you think that I'm doing that, the state's probably 3, and you think I'm going to subtract 1. So I said 5 in order to exaggerate. Anyway, the outcome of this process, the best equilibrium that conveys any information of all, is one in which if the state is 1 or 2, you basically say it's low. It's either 1 or 2. If the state is 3, 4, 5, you say it's high. It's 1 of 3, 4, 5. But there's no way to fully communicate the state in standard theory if the players are self-interested. Okay? So what happens? So this is, again, an icon graph that conveys a lot of data. I'm sorry, let me walk you through it slowly. Each of these rows represents a state. State 1, 2, 3, 4, 5. These are messages. This circle says that when the state was actually 1, the message 1 was chosen most often. The circle is biggest. The size of the circle is the frequency of that state message pair. Messages 2 and 3 were chosen pretty often. This person never exaggerates and says 5. And what you see is these are level zeros. In this implementation of the cognitive hierarchy model, level 0 means just tell the truth. Don't lie. And that's a common outcome. Level 1s add 1 on. So, for example, when the state is actually 4, they say 5. That's actually most common. And level 2s add 2 on. Okay? So there's a tendency, again, the equilibrium theory is that if the state is 1 or 2, you should see 1 or 2s. That's not typically the case. And it's 3 or 5, you should see 3, 4, 5s. That's not typically the case. The behavior is a mixture of truth-telling and then exaggeration. These are, again, this is a lookup icon graph. The width of each rectangle is the number of times they looked at that number, that payoff number. The height is the normalized amount of looking time, total fixation time. And what you see is that when the state is 1, they mostly look at how much they'd get if they sent message 1, how much they'd get if they sent message 2. The state is 3, they look at 3 and 4, and so forth. So this is the aggregate pattern that, again, matches what you saw before. I'm going to come back to this game later. That's why I was telling you about it. Okay. Now, I'm going to show you, in kind of rapid fire, some fMRI results. All of these are subject to the usual kinds of critique. I see these as simply beginning to explore what areas of interest may be part of a circuitry that's doing these different steps of reasoning. And some of these, like our first study a few years ago, was really kind of sloppy, and we've learned a lot since then about how to do better work. Okay, so first, we studied some dominant solvable games. That means games that have a special structure where there's a strategy that's worse for you than another strategy no matter what. You should never pick it. That's like picking a very high number in the 2/3 of the average game. You'll never win. You can do better. If you eliminate those, that often then makes some strategies dominated. If you eliminate those, and so forth. Dominant solvable means iterated application of iterated dominance will lead you to a unique choice that's the best one. Okay? And in the contrast, what I'm showing you is regions that are more active in this experiment, they sometimes choose what to play. They sometimes state what they think others will play. That's stating a belief. And they sometimes state what they think others think they will play. That's a second-order belief. I'm going to ignore that until later. And when they're out of equilibrium, that means, the contrast that's used here, the GLM, to generate these regions of interest is activity when they're choosing a strategy on their own versus guessing what others do. Okay, and remember, a level 1 player, when they guess what others do, is doing no processing at all. Everyone's equally likely. So you'd expect to see a lot more brain activity in choosing relative to believing if you're doing low levels of reasoning. The high-level reasoning players need to really think carefully about what another player will choose in order to do their own choice, and there may be much more convergence in the regions, which means we'll see less activity. So sure enough, when they're in equilibrium, that means that their belief about what others will do is correct. They've correctly guessed what others do, and their second-order belief is correct. The only difference between choosing task and the guessing task is in ventral striatum. And that actually makes a lot of sense because the payoffs when they choose are different than the payoffs when they guess. We didn't work very hard to equalize them. So this may just be a value signal or some kind of a prediction error signal. And when they're out of equilibrium, there's more activity choosing than in guessing in dorsolateral PFC, which activates everything, in posterior and anterior cingulate, and in an area called, John Ullman calls frontal insula. Again, I don't attach, at least for the purposes of this talk, a lot of significance to where these regions are, although they're familiar areas in higher order cognition and reward. But they suggest that when people are choosing, they're doing something different than when people are guessing what others are doing, they're not doing the same thing as when they choose on their own. Okay. Here's a second study from Corselli and Nagel, which really nails things down much more nicely. This is coming out in PNAS soon. So they went really right after this cognitive hierarchy model, can we see steps of reasoning in the brain? And what they used was this beauty contest game, 2/3 of the average game that I mentioned at the start, except they varied the number p. So we looked at p of 2/3, which is here. They varied p from 1/8 to 1.75. And the subjects play a series of these games with different values of p, sometimes against a person, sometimes they're told you're playing a computer that just chooses at random. So the computer case is kind of like just a natural control for reasoning about human cognition versus mathematical calculation. And what you see is some of the subjects can be classified as level 1. They basically just pick p times 50. They act like they're playing that other people are randomizing and they're maximizing against them. So this is the number of choices for all the possible p-values. They're pretty close to just p times 50. Okay. Then there are level 2s, which are shown here. They're basically pretty close to p times 50. They act like they're people who are playing level 1 players who think they're playing random players. So this is just behavior so far. The first contrast is what's going on when they're playing humans versus computers across all subjects. And what you see is, again, a very nice circuit of lots of familiar regions in these types of tasks, some that you've heard a lot about today from Peter and Hilke, and also from Tim. There's a cingulate. In this picture, it looks like it's corpus callosum, but it's a cingulate. Here's the paracingulate region that Peter referred to, ventral medial PFC or medial OFC. This is the bilateral right and left temporoparietal junction that many people think is an important region as part of theory of mind. It may have there's some controversy about that. In any case, when you're playing people in this game versus computers, you're seeing some differential activation and familiar reasons. Here's the closest we've come to nailing down cognitive hierarchy in the brain so far. They divide people by behavior, the first graph I showed you, into people who seem to be choosing p times 50 versus people choosing p times 50. And then, so they divide first on behavior, and then they look at activity in the brain when they're playing humans relative to computers. And in the high level of reasoning players, you see a lot of extra activity in the paracingulate region. Again, fitting nicely with Peter's results. And this just shows you the contrast in the beta plots. And this is from a Tix paper. This shows the blue squares are mentalizing tasks. There's a lot of activity in these familiar reasons. So it looks like there's a kind of neural correlate, as seen in many other games, of doing two steps of reasoning that another player may be acting as if they're playing against a random player. And in the low level of reasoning subjects, you see just a little bit of activity in medial OFC. Okay. Importantly also, they use this term that Megan Abet and I kind of coined called strategic IQ. That basically means how good you are playing games in terms of your performance. And in this game, this is a funny graph, but a higher number here means you're far away from the winning numbers. So you want to be low. 0 means you're winning every single time. And what they see is that as you have increasing strategic IQ, that is lower and lower numbers, you're further and further away from the target, you're closer and closer. There's increasing activity in an area here of medial PFC. So again, this area was picked out by the contrast I showed you a minute ago, and there seems to be a correlation between this strategic IQ or performance level and activity in that region. Okay, this is the most complicated game. I'll try to zip through with the right trade-off of comprehension and speed. A yard sale is a term that's used in the English for this. Actually, this is more like a flea market, slightly different. A yard sale is when people have a bunch of junk in their garage and they want to sell it to other people. And they have two motives, which is to get rid of it. So the cost to the seller is essentially zero. They really don't need this stuff. But they also want to make the most profit. So typically people set up these card tables and they come by. And if you're a buyer, you come by and say, well, how about $5? And the seller's job is the seller would sell it for $1. But they want to maximize profit. So the seller's job is to try to figure out how much you would really pay and either counteroffer and say, well, okay, how about $8? Or maybe accept your offer of $5 or something like that. Okay. So in terms of the basic game theory structure here, the idea is that the seller has a cost of 0. They will sell for any number if they have to. The buyer has a value v, which comes from a uniform distribution 1 to 10 integers. Okay? The buyer, so this is a game of private or asymmetric information. The buyer has a number the seller would like to know and does not. And the seller is going to try to make a guess from something the buyer does about what that number is. It's kind of like the states, the 1 to 5 states game I showed you before in strategic information transmission. So the buyer first gets their value v. They send a suggestion s, like, how about 6? I'll give you 6 for this ugly lampshade. The seller then gets the suggestion. They don't know the value v, they just know the suggestion. And they have to make a counteroffer of price p. And the trading is automatic and very swift. If the price P is below the actual value, the trade takes place. The seller gets P. This is a typo, I'm sorry. The buyer gets V minus P. It gets the surplus, the difference between the most they'd pay and the amount they pay. If the price is above the value, no deal takes place. They get nothing. Okay? So we struggle with this a lot. When we first started designing the study, we had all these complicated things. Those of you like Roger who know a lot of game theory, there are many extremely complicated bargaining games you could pick. We kind of stripped it down to the most simplest thing that wouldn't be too trivial and which would be workable in imaging and some other, using other techniques. So the idea is that the buyer knows something the seller wants to know, and the seller is trying to infer it from this suggestion. And importantly, in order to disable reputation effects, which complicate life a lot, we've studied those behaviorally quite a bit in the past, but wanted to avoid it here, they don't actually find out if the deals take place. So they're actually not getting any feedback. The task is kind of boring. They're just going through. That's important for what comes next. Okay, so it turns out that you can classify the buyers into 3 clusters using a formal cluster analysis. By the information revelation, that's the slope of the regression of their suggestions against their values. So if I'm the kind of person when my value is 2, I say, well, how about giving me a price of 1? When my value is 10, how about a price of 5? I'm revealing a lot of information with that pattern. That would be a high slope up here, and a high R-squared. So R-squared is on the y-axis, how well this regression fits, and information revelation here. So the blues are truthful. These are people who reliably give a suggestion which is a good clue to what the true value is. The greens are uninformative. In fact, the game theory here predicts that no, you shouldn't reveal anything about your suggestion. The buyer should just ignore what you say and offer a price of either 5 or 6 to maximize expected profit. So the greens are people who have low R-squareds, and typically the information revelation slope is around 0. The reds are the interesting ones, although notice they're the smallest group in number. There are 56 subjects here. This is a collaboration with Reed and Megan Abbott and Terry Lorenz too. Reed Montague, some of you know, in neurosciences at Baylor Medical School in Texas. They have big hair, big trucks, big guns, and big sample sizes in brain imaging. So, but that's actually very helpful here too, because in a way we really want to study the individual variability and to do rather than typical random effects analysis. So to do that, you just need a lot of subjects or some way of screening or generating healthy variability. So these red ones we call strategists. These guys are really clever. Again, they're few in number, but they're very interesting. They have a negative coefficient. And what it is they do the opposite. When their value is really high, they send a low number, trying to get a really big profit. So if my value is 8, I might send, well, the most I can pay is 2. Because if you then name a price of 2, I've made 6 units of profit. Okay? But then, why do I believe you? I believe you because when my value is 2, if my value is 2, I'm never going to make a lot of money anyway. So I say, oh, I'm willing to pay 8. And the strategists know that the buyers then say, oh, in that case, well, if you're willing to pay 8, I'll charge you 8. But the trade, they don't know if the trade actually takes place. We know, but they get no feedback. So the strategist is basically, here's an example here. The strategist is choosing a series of suggestions over the last 30 trials of the game. They play 60 times, which have a frequency so that they sometimes pick really high ones and sometimes low ones. And in fact, this is a truth teller or an incrementalist. This is the actual distribution of suggested prices from someone who's revealing a lot of information. What they're doing is when their value's high, they give a high suggestion. When their value's low, they give a low suggestion. The strategist does exactly the opposite. Exactly the opposite. When their value is high, they say low. When their value is low, they say high. But their profile looks exactly like this incrementalist. So if you're playing this game, it's like, wow, this guy sometimes, tells me the truth that this value is really high. Sometimes it's low, and I have to give him a break. And they're taking complete advantage of you. Okay? So they tie this to a cognitive hierarchy model. You don't have time, nor do you need to read all this information on the screen. The point is that the way to make sense of this is that the sellers think that there's some buyers who reveal information with a ratio alpha. Alpha is sort of how truthful they are. If alpha is 1, they just tell you the truth. If alpha is a half, they cut their value in half. And the level 2 buyers think they're playing sellers who are inferring alpha from this whole sequence of suggestions they see. Okay? So they're playing a strategist who sometimes says 2, 1, 8, 4, 3, 2, and they think, well, this guy's giving me a lot of information about value. His alpha must be high. Therefore, I'm going to price very fairly. So the level 2 buyers, the strategists, think they're playing level 1 sellers who think they're playing level 0 buyers and are Bayesian updating on the value of this alpha coefficient. Okay, and just one little piece of fMRI to show you. This is actually 2 slightly different contrasts. The bottom one is just strategists minus non-strategists at the time of decision, the time at which they send a suggestion. And you see activity in the retrosplenial cortex. This is a correlation of the slope coefficient of the information revelation regression, the regression of suggestion on value, and it picks out almost exactly the same region. What is retrosplenial cortex? Stan, close your ears. This is classic reverse inference. We didn't particularly expect this region, but it's here, so we can not do anything or speculate. At this point, all we can do is speculate, and then think about further tests that would be natural follow-ons. The retrosplenial cortex seems to be involved in episodic memory. There's some lesion studies showing that you knock out different types of memory and learning in the region. Also, early evidence suggested negative emotions. And the most compelling evidence from Eleanor McGuire and others is that it seems to have to do with cognitive mappings. So you show people films of a room they have to navigate and ask them to imagine navigating the room, and you get activity in retrosplenial. Our group is kind of negotiating over what we think is really going on here, how to write a paper, and what to do next to really disentangle these explanations. I see these studies as really not having conclusions, but having hypotheses for future studies you would like to do. And interestingly, this and a couple of other regions, the precuneus and Coleman, there's only 3 or 4 regions activated more strongly by strategist thinking versus non-strategists. There are a lot of areas that are activated positively by information revelation. When more information is being revealed, there's dorsolateral PFC, cingulate, caudate, and we haven't figured out what that means here. Okay, finally, a couple of applications and conclusions. So, again, my perspective, as I hope you've sensed, is that I started as an economist thinking about these mathematical constructs and things like equilibrium concepts, and we're trying to drill down to learn more about the mechanisms that are actually instantiating this behavior at the neural level in order to understand the economics better and to be able to then do practical things. So one thing we study is economic value. That means if you created an artificial subject who used the cognitive hierarchy model to play games with other humans, would they do better or worse? The amount better that they would do, if it's positive, is a measure of sort of the economic value of theories. A second thing I'll talk about in a minute is inferring private information, and I have a paper which I love to talk about, but just it has nothing to do with neuroscience and has no time today, on moviegoers' reactions to cold openings. The simple idea there is just this, which is in the U.S., in our sample, which is all major movies in the last 6 years, about 10% of the movies are not shown to critics in time for the critics to publish a review. Are they good movies or bad movies? they're bad movies, as judged by critics and by moviegoers who went and saw them. The critics and moviegoers actually agreed to a substantial extent, like a correlation of 0.8. Then if the studios realize that people know that unreviewed movies probably are bad, why don't they just let them get reviewed? The answer, we think, is that they think they're fooling some of the moviegoers who think, oh, there was no review. Well, I don't think that means anything. And this can be fit into, again, a cognitive hierarchy model in which some percentage of the moviegoers consuming the critic information are not making the correct inference that no review is bad news. And that actually fits the field data pretty well. It turns out that that helps you explain some things in box office reactions. The example I will tell you a little about, remember the exaggeration game or bullshit game? That's where states 1 to 5 are observed by a sender. The sender sends a message. The receiver gets the message, doesn't know the state, has to figure out how much exaggeration was going on. We can ask the following question. Suppose you use the lookups of the senders. We know what they look at. We know, for example, if the state is 4, they look at the payoffs associated with state 4 a lot. And pupillometry. Could we then say, gee, based on what they were looking at, the true state is 4, even though they said 5. And then we didn't actually do this in the experiment. It's an after-the-fact, ex-post exercise. And then we say, if I was a subject forecasting the true state from what the other person looked at and from their pupil dilation at the time at which they announced the message, could I make more money? The actual earnings the subjects have is 85.5. The maximum they could get if they completely told each other the truth is 109.1. Using this mechanism, the kind of cognitively aided amount you could earn is 92.5, which is halfway between. So using these data, you could get halfway from where the subjects actually are to essentially the maximum possible earnings. Now, we don't know something very interesting, which is if you were a sender and you knew that what you were looking at on the screen was being measured and recorded and used as information, do you then deliberately look away? It might. This is very much like lie detection and other things, right? It might turn out that if you deliberately look away, the way in which you look away actually gives you away, and you can't really protect yourself. So we don't know. These are things that we can study later. Okay, so to conclude, what I've laid out today is what's called the cognitive hierarchy approach. There's a lot of gory detail. Quite a few people are working on this in various ways. And I tried to show you 4 types of data. Again, I apologize. I wish there was more neuroscience here to talk about. It's just not very far along. There's data from lab experiments, like this one, data from field experiments run by newspapers, data from a field data set that had no experimental component, but we recreated in the lab in Sweden, and a little bit of imaging data. There are lots of open questions. Are there distinct types in the brain? Are people born level 2s? Almost surely not. We do seem to find some kind of persistence of individual differences if you have people play a whole battery of games. How they're classified on the first 10 games correlates modestly with how they're classified in the last 10. Probably it has a lot to do with general intelligence and working memory as well. We'd like to know a lot more about, the natural thing is to link these to theory of mind regions like parasingulate and TPJ, having to do with beliefs, intentions, and attributions. In the area of disorders, you can think of lots of disorders which have, as part of the symptomology, something having to do with strategic thinking, either paranoia, mistakenly thinking people have ill will, gullibility, not being paranoid enough, and we heard a little bit earlier about the role of social reward and social learning in autism, in at least HFA, that Angela talked about. And finally, the opposite, in economics, we're interested not just in things that are broken, but things that are terrific. So you could easily imagine studying, expert poker players and things like that to see, what happens when people are highly experienced and extremely good, very high up in the cognitive hierarchy. That's something we haven't specifically attacked. It's an obvious thing to do. And I have a lot of collaborators who did all the work. Thank you.
I could not refrain from asking a question which might also be addressed to the previous talk. In assuming that subjects make these high-level hierarchical models, this involves increasingly complicated representations. And so sometimes it is not a surprise to see areas like mesial prefrontal cortex or anterior cingulate that are associated with cognitive effort. I was wondering if any of your experiments were separating theory of mind from effort, which could occur outside of the domain of mentalizing.
Sure. Well, most of the studies, and also there are a few studies, Peter mentioned some like Gallagher and McCabe. There are a few studies that I haven't I left off because they weren't as tightly linked to this idea of steps of reasoning in a parametric way. Most of the studies do have these you're playing a computer control task. It's true, I don't think any study has varied the complexity of the computer's algorithm, which in some ways would be the cleanest control. You're playing a computer that's choosing randomly, you're playing a computer that's thinks it's playing humans choosing randomly, and something like that. I think, probably a lot of what you would see, for example, if we just did these types of tasks and you look at activity, a lot of it is going to have to do with just general mental effort, representation of maintenance. And how much of it is kind of special to playing other people and maybe varies with the nature of the other people would be very interesting to study. And also, you could well imagine that these processes are sensitive to who it is you're playing. If I'm told in a 2/3 of the average game you're playing a person with a PhD in game theory, your representation of their skill is different, and that should generate differences.
Other question? Yes, Tim.
So again, I'm not sure if this is a question for you or for Peter, but maybe you can answer it between you. So
if it's hard, it's for Peter.
I don't know. So in Peter's study, he has activation in the dorsal medial prefrontal cortex and in the posterior SDS, and you have it in the temporal parietal junction. It's in a similar place. In various studies of theory of mind, like in Rebecca Sachs's work, for example, it is that TPJ region that is encoding the belief state of others, rather than just the fact that you're playing against other people and not the dorsal medial region. But yet in your work and in my work and here, that DMPFC is doing that. But in Peter's study, I'm sorry if it's a complicated question, in Peter's study, the TPJ region is always coding for the most complex thing, even in subjects who won't go on to use that. But the DMPFC is telling you what the subject will eventually do. So, firstly, what does the TPJ region do? Does the TPJ always code for the most sophisticated strategy, even in subjects that won't use that in your study? And if so, isn't that a bit amazing? Anyway, so what does the TPJ do is a simple version of that question.
Well, it's true in the Corselli-Nagel paper, which I had a chance to work with them on, and I just didn't think it would work as cleanly as it did. Otherwise, I would have participated. So it's their study, which I like very much. Yes, you're right. They find that both bilateral TPJ, Sachs, I think, is arguing right TPJ may have some extra special role in all subjects playing humans versus computers. I don't recall in their paper, maybe it's in supplemental material or something, whether that general activation is entirely due to the higher level subjects or not. It may be that the higher level activity is so strong that it's coming across in random effects. There's also some work you probably know by Jason Mitchell and others, I think, arguing that you also get similar activity in tasks having nothing to do with human cognition in reorienting, sort of in Posner tasks, and that suggests that either thinking about other people's beliefs requires some sort of fundamental reorientation, or, obviously there are many to one mappings as well as in what these areas do.
In your task, you don't have something like John and Peter have, where you have people that aren't going to use a high-level strategy, nevertheless maintaining a representation of that high-level strategy in their brain somewhere, which is particularly intriguing from Peter and John's study. Yeah,
in most of the studies I showed here, keep in mind there's no actual feedback, and the reason is that most of these studies wanted to isolate just the pure reasoning process, knowing you're playing a person versus a computer with some kind of other conditions. Basically, it's not that the social learning isn't interesting; it's too interesting. At this point, we felt it was a Pandora's box. There's too much stuff going on, but obviously, model adjustment and social learning and influence value are super interesting things. I don't know if that's next on the agenda because it's still kind of intimidating. But in Peter's task on the worker shirk type game, they are playing each time and getting feedback, and it may be that these regions are then unusually active in the process of model formation and model updating, which we're probably just not seeing in the studies with no feedback. So they're maybe two entirely different paradigms, really.
I think Just before we go to the next speaker, I have maybe two comments. The first one is that the normal form game associated with the garage sale experiment is somewhat simpler than what you would do if you were describing the bazaar in Marrakesh, when people do it a number of times, I suppose. The second point is only a personal remark. I have been involved in the 2/3 of the mean game. I will tell you maybe later how. But it's called the beauty contest game, and I think it's. I tend to believe that it's a wrong appellation, wrong word for describing what it is, because I think the beauty contest game of Keynes has not this structure at all. At least that's my opinion. But
well, you invented it, didn't you?
no, I did not invent the game, but I taught this game to Rosemary Nagel.
Right.
Yeah.
Right. Yeah, well, actually, briefly on that point. So, yeah, I didn't have a chance to put the passage up, but in Keynes, he has a very famous passage where he says the stock market is like a beauty contest, in which people are anticipating what others think the value of companies is, and anticipating what others think others anticipate, and so forth. And the reason we use that term was that Keynes doesn't specifically talk about timing, but clearly I think he has in mind a dynamic model in which the goal is to sell at a time when others haven't decided to sell yet, which is the role of, for example, you can do the beauty contest game where P equals 1, so that everyone wants to be as close to the average as possible. And that sort of also falls with the class case quite.
No, I think that the Keynes
different.
beauty contest is rather correspond not to 2/3 but to 1. Everybody wants to do to give something that is closer to the mean, and it has a very different structure.
Right.
But
Correct.
That's,
yes. Yeah. Your point is
terminology.
Yeah. And actually, to be fair, we called it the P beauty contest game.
Yeah.
In order to sort of calibrate across P that the structures really are quite different. But it's kind of an ugly term.
Okay. Thank you very much.